Engineer Russ McMillan works for the Ministry of Defence team responsible for Britain's next-generation nuclear submarines. In this video clip, he talks about the principles of submarines and buoyancy.
Okay, so I thought I'd just start by talking through a little bit about what a submarine is, what the different main parts of a submarine are, and then I can talk a little bit more about the specific things that I work on. The UK only has nuclear submarines now. Now that effectively means that the submarine's powered by a nuclear reactor. On our latest class of a submarine, Astute, the amount of power that a nuclear reactor generates would be enough to power a city the size of Leeds, and that's all contained within a pressure hole that's about 10 metres diameter. So within the submarine, in the middle, you've got a nuclear reactor that's generating lots of heat. It's a relatively conventional method of taking that heat and doing things with it. So the heat is used to generate steam, and then from that steam you either turn turbines, which give you mechanical power to drive the propeller and drive the submarine through the water, or you drive another form of turbine which generates electricity. So reactor's sort of in the middle, and then you've got an engine room in the back, and the engine room's generating mechanical power to drive your propeller and electrical power to support the rest of the submarine. So broadly, the back half of the submarine is all to do with engines and the engine room and things that keep people alive within the submarine. So you obviously need to generate your own oxygen and generate your own fresh water, and all those kind of things are within the confines of the submarine. And then the front half of the submarine is sort of where people live and where the torpedoes are and where the submarine's commanded from. The most fundamental thing about a submarine is how it submerges. So I was going to talk a little bit about buoyancy and how the submarine ensures that it submerges and surfaces and all those kind of things. So in its most simple form, if you consider the submarine to be a cylinder of the order of 10 metres in diameter. So this is a big steel cylinder with two domes on the end, and it's designed to resist huge pressures at depth. So Archimedes' law, the buoyant force on an object when submerged is equivalent to the weight of the water it displaces. So you can run a relatively simple calculation in terms of what's the buoyant force on that object. And to do that, we obviously need to work out the weight of the water displaced, which means working out the volume of the water displaced. So if we take a 10 metre diameter cylinder, then the volume of that cylinder is going to be the circle on the end, pi r squared, times the length of the cylinder. And if we say the length of the submarine is broadly 100 metres, then we're going to have, if we approximate pi to 3.14, times it by the radius squared, then times it by the length, then we end up with the volume of the submarine, which in this case is 7,852 metres cubed. However, of course, on the end of each of the faces of the cylinder, you've got two spherical domes. So you need to add two of those on. The two spherical domes together form a sphere. The volume of the sphere is 4/3 pi r cubed. So we need to add that on, again approximating pi to 3.14. Radius again is 5 metres. So you've got 4/3 times pi times 5 cubed, and that gives you an additional volume of 523.3 metres cubed. If you add those two together, you end up with an overall volume of the submarine of 8,375.3 metres cubed. So from that's the volume of the water we're displacing. A metres cubed of water weighs a tonne, so it's a relatively easy transition. So what we're effectively saying is that we're displacing 8,375 tonnes of water.
In round figures, a submarine weighs about 8,000 tonnes. So as it floats in the water, there is a downward force in newtons of 8,000 times 10 to the 3 times gravity. This is opposed by the buoyant force due to the weight of water displaced, which Russ has just calculated as 8,375.3 tonnes.
So you can see where the submarine is just sat doing nothing, the buoyant force is greater than the weight of the submarine, so it's going to float. So what you want to do is ensure that the submarine submerges, and the way you do that effectively is by decreasing the volume of the water that the submarine displaces. So within the submarine you have a series of tanks called ballast tanks. They're connected to the sea and they've got pumps, so you can pump water in and out of the submarine. So if you want the submarine to sink, you effectively need to pump in enough water so that the volume of the submarine decreases to such an extent that its weight is greater than the weight of the water it's displacing. And in this instance, it's probably easier to think about these tanks as effectively being connected to the sea. So when you fill the tank up, the volume of the submarine just decreases because this is all seawater in this space now. So how big do we want the ballast tank? Well, clearly we've got a difference of 375 tonnes. So what we want to do is put 375 tonnes of water in there. So we can pump in 375 tonnes. At that point, the submarine will be neutrally buoyant. If we continue to pump more water in, then the submarine will sink. So that's the sort of basic principle of buoyancy and how ballast tanks work and how the submarine submerges.